The team at Deep Learning Analytics brings you this set of video notes on screening and stabilizing 3D t-SNE embedded image activation manifolds. Authors of this work include Michael Trammell, Priyanka Oberoi, Jennifer Sleeman, and John Caulfield. This work was supported by DARPA, and the views, opinions, and/or findings expressed are those of the author and should not be interpreted as representing the official views or policies of the Department of Defense or the U.S. government. This work is motivated by the widely recognized phenomenon in deep learning of attaining higher image recognition accuracy on object classes that are well represented in the training data. In this result, we trained a convolutional neural network architecture to recognize many different classes of objects, classes with considerable overlap and redundancy in their features, and with a wide variety of training observation counts per object class. It was observed that object classes represented by more training data typically had higher accuracies on the held-out test data. In this example, the convolutional neural network only achieved 65% accuracy when it was given less than 100 examples of a particular class of objects as training data. However, for all object classes with more than 2,000 examples, accuracy was better than 90%. So in summary, error rates on sparsely observed object classes are consistently worse than error rates for densely observed object classes. The dependence of validation error on number of examples seen during training also leads to slower learning for sparsely observed object classes. In this experiment, the green curve shows that deep architectures quickly learned highly accurate recognizers when sufficient object class instances were observed in training. However, as can be seen with the red curve, learning slowed and recognition performance degraded when only 10% of the same objects were seen in training. Supplementing the training data by generating new training images is possible, and recent breakthroughs in generative adversarial networks, or GANs, have made great strides in image generation. However, it may be simpler to understand and even fill in training gaps in the lower dimensional image manifold space than in the native image space, or pixel space, using manifold theory. Visualizing this relationship between image manifolds, convolutional neural networks, and embeddings is the focus of this work. Manifold theory posits that high-dimensional objects, like images, live in a lower dimensional space that preserves salient properties of the high-dimensional image space. In this example, there is an instance of a particular object class in the real world that is observed by a sensor producing a digital image. That digital image is represented as a 2D location in an embedded space and is known as the manifold representation of that image. The 2D location depends on many things, like what object class is in the image and salient features such as the pose of that object and the look angle from which it's viewed. A different image of the same object class exists somewhere else on the manifold representation. And images for that same object class viewed from similar look angles would produce similar 2D coordinates. And as images of this object are viewed from many similar look angles, if those look angles are packed densely enough, they may paint out an approximately 1D manifold over those look angles. But if only sparse training observations of this particular object class are available, such as the instances highlighted in red, it may not capture all of the meanders of the true 1D image manifold. Here we show the true underlying manifold in black. When deep learning algorithms see training data densely packed enough, like the instances in green, they can do a good job approximating that true manifold. But when they only observe sparse training data, like the instances in red, they can fail to approximate that true manifold. This was the behavior we observed in our experiments. That deep learning recognition algorithms trained on dense imagery, the green curve, learn faster and converge to lower error rates than when trained on sparse data, the red curve. Visualizing manifolds may help us identify where the image manifold representation is incomplete. However, image manifolds are high-dimensional objects that cannot be visualized directly. Therefore, the following describes a process to generate approximations of image manifolds with deep learning and embeddings. A common deep learning task is to label images to describe what object class is in each image. For a collection of images of different object classes, or labels, here we'll denote each distinct object class using a filled colored circle. So we can have up through n different kinds of objects. And we would typically pair the images with their label. The images are represented as open green circles, which means that the label data can be separated as pairs per object label. We can then split this into a labeled set of training data for supervised learning and set aside our test data. We can then train a deep convolutional neural network, or deep CNN, that excels at recognizing new images. In the past 5 years, this type of convolutional network has been shown to perform better than others at accurately recognizing new images that were not seen during training. The deep CNN converts its input image into its best guess at the label for that image. Here we see 3 input test images that were not seen during training being converted into 3 different labels, 1 label per image. But a portion of an accurate deep CNN can also be used to reduce the dimensionality of the representation, so we only retain the most salient features. We call this the deep CNN learned representation. It takes images as input. These images are higher dimensional representations of object class instances, usually on the order of 10,000 dimensions. And the deep CNN learned representation converts them into lower dimensional summary representations called activations, typically on the order of 100 dimensions. But while dimensionality is reduced from tens of thousands of dimensions in images to hundreds in activations, there's still a question of how we can use these activations to visualize image manifolds. Specifically, how can we see the manifold relationships between object classes in the activation space? Our answer is 2D or 3D embeddings. This question can be formalized as, do 3D t-SNE embeddings of learned activations preserve image manifold properties of the data? To answer this question, we visualize 3D t-SNE embedded activations from a deep CNN trained to recognize different object classes, as we described previously. The 3D visualization of t-SNE image activations is annotated to illustrate 3 things. First, that the embedded activations of instances of different object classes fall on different manifolds. Second, that instances of learned object classes form piecewise continuous 1D submanifolds. And third, that embedded 1D submanifolds form continua over the look angles. Here we see a 3D t-SNE embedding where images from object classes and the background are embedded into 3D. The 1D submanifold structures are apparent even in this image. Note that the process of t-SNE embedding activations is unaware of the object class labels. The embedded structure seen here is inherited from the deformation and compression of the high-dimensional image pixel space into the activation space by the learned deep CNN representation, which is then further compressed in dimensionality by the t-SNE embedding. In this visualization, we color-coded each embedded input image with its object class type. It's worth noting that the 1D submanifolds are indeed separated by their class labels, also that the large cluster of background patches in the middle of the visualization does not retain the structure, as these patches are effectively random draws of different background patches with no consistent pose or look angle relationships. But because backgrounds can contain objects that look similar to one another, Even the background patches have developed some complex manifold structure. In this visualization, we omit the background to focus just on the look-angle relationships. Because we know the look angle of every object class instance, we plotted their angle with a short line segment in this visualization. So specifically, manifolds for each object class are composed of piecewise continuous submanifolds that vary approximately continuously over ranges of look angles. In 2017, John Launchbury of DARPA's Information Innovation Office developed a summary of AI called DARPA Perspective on Artificial Intelligence. DARPA incorporated our results into their perspective. The presentation can be found here at http://www.darpa.mil/attachments/aifull.pdf. And slide 12 incorporates our work. Specifically, John Launchbury described recent AI progress in waves and wrote that each manifold represents a different entity, or object class, and understanding data comes by separating the manifold. As can be seen, the manifold visualization was generated by deep learning analytics. John Launchbury's own comments can be found on YouTube on DARPA TV.
Data is grouped together to clump to form a substructure within a much larger embedding space. And it turns out that when we're dealing with the natural world, the data that we care about forms these clumps. Let me show you an example. In this rotating sphere that you see, we've taken data from a natural source and brought it down to 3 dimensions. And you can see that the different kinds of data have clumped together. Sometimes they're in stringy sort of shape, sometimes in sort of fuzzy sponges. That red shape that you might see in the middle is actually sort of like an orange peel shaped two-dimensional thing that curves in on itself. Each of these manifolds, each of these clumps represents a different entity. And the way that an AI system will understand the data is it will separate the different clumps. Now you can imagine that it's really hard to describe one clump from another by saying, well, if it's up in the top left and shaped in this kind of set, that's very difficult in first wave technology to be able to describe. So second wave technology needs to find a new way to be able to separate these things. And what it does is it starts to take the space itself, the data space itself, and stretches it and squashes it.
So we thank DARPA for their interest, and we are excited to continue this research. We saw that embeddings formed continua over ranges of look angles, but image manifold theory predicts that object class manifolds should form complete look angle loops for a given object if it is collected over the full 360 degrees. In this experiment, we curated a corpus of images of different object classes with an instance of each class collected over 360 degrees. We use this data to explore how well embeddings preserve look angle loops present in the data and outline how to efficiently screen embedding parameters to reliably recover this manifold structure. We begin this investigation with a new image corpus that was composed of 12 unique object classes, each of which was sampled thoroughly over the full range of look angles. Specifically, every object class image has a look angle neighbor that is less than 10 degrees away. An initial t-SNE embedding of this new data using the same sklearn module illustrates that while some of the submanifolds already form nearly uninterrupted loops, as is predicted by manifold theory, many of the submanifolds still contain distinct gaps. As we see here, the example in red is an instance of a submanifold that looks like it has nearly uninterrupted loops, whereas the following example in green has distinct gaps. With a more careful design of the embedding, we can do better. Given the size of our data and our goal of quickly and intuitively visualizing these manifolds in 3D, we combined 2 t-SNE packages. multicore t-SNE, which is fast but currently limited to 2D embeddings, and sklearn's t-SNE embedding, which is slower but can handle 3D embeddings. First, we screened multicore t-SNE's perplexity and number of iterations parameters. We did this to quickly find embeddings that preserved image data properties like look angle loops. We visually inspected all of the embeddings and chose the one that looked most intuitively correct. One thing we wanted to see was a qualitative preservation of the look angle loops in the input data. We chose a perplexity of 50 and an iteration count of 500 based entirely on a visual inspection of the results. We then tested that parameter choice for reproducibility. We generated multiple 2D embeddings with these same parameters. This visualization confirms that while each embedding is unique and manifolds of individual classes move around with respect to each other, the individual object class manifold shapes remain qualitatively similar from one embedding to the next. Looking at one of the 2D embeddings more closely, we can see that, like the original 3D embedding, the 1D object class submanifolds are still relatively well sorted by look angle, and often form nearly complete look angle loops for each object class. In order to generate a 3D version of this 2D multicore embedding, we first selected 3 multicore embeddings with the chosen parameters at random. We then concatenated one dimension from each of these multicore embeddings into a single 3D embedding, which we call a 2.5D embedding, since it's really a 3D embedding cobbled together from multiple 2D multicore embeddings. We used that 2.5D embedding to initialize sklearn's t-SNE embedding module. sklearn's t-SNE then refines the initial 2.5D embedding into a high-quality 3D embedding, which effectively distributes manifolds over the entire space and preserves the 1D loopy manifolds. Note that when we use straightforward random initialization of embeddings in sklearn, it was a much slower process to find an embedding that preserved look angle loops. Our approach combines the speed of multicore t-SNE in 2D with the ability of sklearn's t-SNE to embed in more than 2 dimensions. Once again, we draw the actual manifolds to see that this does indeed provide a significant improvement over the previous embedding, which developed gaps in look angle loops. In conclusion, careful t-SNE embeddings of activations from deep convolutional neural networks preserve image manifold properties. While t-SNE embeddings vary from embedding to embedding, they produce consistently tight 1D manifolds for object classes. Rapid multicore t-SNE parameter screening and reproducibility testing of 2D embeddings enables visual search for robust 1D manifolds with look angle loop structure. Careful 2.5D initializations of 3D t-SNE embeddings reliably inherit t-SNE variability while providing an initialization scaffold for 3D t-SNE embedding that manages to preserve 1D image manifold properties and look angle loops. These findings support further research into completing manifolds in the low-dimensional embedding space in order to translate those newly found meanders into images that can improve performance for sparsely observed classes in deep architectures.